Okay, good afternoon. Welcome to this session about Microsoft Cognitive Toolkit. My name is Cha Zhang. I'm a Principal Applied Science Manager at Microsoft AI and Research. So let me start by giving you a brief introduction of Microsoft Cognitive Toolkit. In this talk, I'll be using either Cognitive Toolkit or CNTK as a brief for the toolkit itself. So CNTK is Microsoft's open source deep learning toolkit. It's open on GitHub.com, Microsoft CNTK. This was created originally by Microsoft speech researchers back in 2012 and was named the Computational Network Toolkit. For those of you who kind of want to learn a little bit more about this history, so when deep learning just become really popular back in 2011, the first breakthrough was actually in the speech recognition area. It was researchers at Microsoft Research who first figured out that you can use deep learning to significantly improve the speech recognition accuracy. So this is the toolkit that was built by the same set of researchers at MSR. We decided to open source this toolkit. It was first open sourced on Codeplex in April 2015, and then we open sourced it on GitHub with a much more permissive license, MIT license, in January 2016. So currently, CNTK has about 12,000 GitHub stars. This is currently third among all the major deep learning toolkits. We are behind TensorFlow and Caffe, but we're ahead of many other toolkits like MXNet or Caffe2 or PyTorch, etc. We have 140 plus, close to 150 contributors from MIT, Stanford, NVIDIA, Intel, and many, many others. So the Cognitive Toolkit is mostly used by Microsoft internal deep learning workload currently. We have almost all the divisions inside Microsoft using CNTK. That includes Cortana, HoloLens, Bing Ads, Skype Translator, the Windows division, Office division, and cognitive services, and of course Microsoft Research as well. One of the things that we're very proud of is that the toolkit is basically identical internally and externally. So if you get a copy from GitHub of CNTK, you'll be essentially using exactly the same copy of toolkit that's being used by all product teams inside Microsoft. So from the very beginning, CNTK was built as a first-class toolkit on both Linux and the Windows. For a while, it was kind of the only toolkit that supports Windows natively. CNTK also has Docker support. We have a rich set of API. For the toolkit itself, it's mostly implemented in C and C++ for both training and eval. So this is slightly different from many of the other toolkits, which usually have a relatively small C++ kernel, and the majority of the functionalities are implemented in Python. In CNTK, most of the functionality we implement is in C++. On top of C++, we have a relatively thin Python API. So we have a low-level API that's basically Swig-generated Python code. And we also added on top a high-level Python API that's very, very similar to Keras. And it's very easy to use. We also support R and C# API for both training and eval as of this September. So we just actually released both of them, which I will go through them a little bit in more detail later. We have UWP support, Java support, and Spark support. We have a bunch of built-in readers for distributed learning. Just to explain a little bit, so in deep learning training, when you go on to production scale, usually you need to train your production task on multiple GPUs or across multiple machines. And reader, which essentially takes care of how you read all the data from disk, randomize everything, making sure when you have distributed training, every node of the GPU be loading different data, etc. So these are automatically taken care of by the built-in reader inside CNTK. Since V2.0 in June this year, we also have a Keras backend support, and we also added some model compression functionality, which allow people to quantize a deep learning model into, say, 1 bit per weight. And that can speed up evaluation dramatically by probably up to 30x. And you can run for example, AlexNet on a Raspberry Pi at maybe 20 to 30 frames per second. The latest version of CNTK is currently V2.2. This was released a week ago, September 15, 2017. So one thing that's kind of we're very proud of CNTK is its performance. So this is a performance toolkit benchmark basically done by a third party, completely independent of any of the toolkits, a university in Hong Kong Baptist University. And they have been running this benchmark for many versions. And this is the latest version, is version 8. So in this particular version, they have been comparing 5 different toolkits: Caffe, CNTK, MXNet, TensorFlow, and Torch. They have been comparing across different network types, like fully connected network, AlexNet, ResNet, and LSTM. So you can see from this table that essentially Cognitive Toolkit kind of beat everybody across the board on all the network types. And in particular, for the LSTM, which is a recurrent network, we are hand-on like 5 to 10x faster than any other toolkits out there. So if your application involves, say, speech, audio, or natural language processing that's going to be sequence dependent, then I think CNTK is your most natural choice for doing deep learning training. Another thing that CNTK is really good at is its scalability. Because Microsoft is kind of the first company who figured out that speech recognition can be improved quite significantly by deep learning. And as a result, the speech production team used this toolkit very early on. And we quickly realized that for any production workloads, we have to run this training across multiple GPUs and multiple machines. So this particular slide is actually pretty old. It's December 2015. And you can see that CNTK is the only toolkit that can run on 2 machines, each with 4 GPUs equipped, so total 8 GPUs. And you can see basically all the other toolkits cannot run anything in such a setup. That was December 2015. And we have been working really closely with NVIDIA, for example, that making sure that the latest communication API coming out of NVIDIA is adopted in CNTK very early. So this is a slide, I think it was last year's GTC when Nickel 1.6 was announced. And you can see that basically with CNTK, you scale from 1 GPU to 2 GPU up to 8 GPU on a DGX1. We're getting almost linear scaling up. And for GTC this year, which is May 2017, NVIDIA demonstrated in the conference that CNTK is probably the first toolkit that works with Nickel 2.0. So Nickel 2.0 compared with 1.6, the difference is that it now allows you to communicate across machines rather than just communicate between the GPUs on the same machine. So now we can scale up to more than 8 GPUs. And you can see that basically this figure shows if you use the 8 P100 or 8 V100, or you go up to 16, 32, 64 Volta GPUs, and you can see the speed up really nice. So Nickel 2 integration has also been released by CNTK. This is released basically version 2.2. We have it, so you can play with it yourself. And for those of you who want to scale even further, we have actually already also experimented that. So this is news from December last year, where we work with Cray. Cray is a supercomputing company. So we have worked with them to scale CNTK to over 1,000 P100 GPUs. So you can see basically the toolkit is extremely flexible to handle large workloads. So next, let me give you a kind of an overview of what is CNTK. And before that, I'll tell you a bit about the current CNTK, how do you install, etc. So installation for CNTK is very simple. What you need to do is just do a pip install with a URL, which is going to be a wheel file. We have a bunch of precompiled binaries you can use. The difference between CNTK's pip install and other toolkits is that we embedded all the dependent libraries inside this wheel. So when you install, you don't need to, say, pre-install CUDA yourself, etc. Basically, you just download and just run, and everything is ready to go. CNTK offers a long list of tutorials. So we have, I think, maybe 20 plus tutorials. And these tutorials are not just explaining CNTK. They actually explain basically deep learning concepts very well as well. So you see these topics covering basics from multi-level perceptron to convolution network to LSTMs, or to then later to more sophisticated models such as neural style transfer, generative adversary neural network, etc. So this is a really good resource for you to learn about deep learning and the CNTK. And for those of you who doesn't have your own, say, laptop that's capable of running any of these tutorials, if you just have a browser, you can run some of these tutorials free, pre-hosted on Azure. And so you can just go to this particular link, notebooks.azure.com, CNTK libraries tutorials, and you will just be able to run a subset of the tutorials. These Azure machines are CPU-based machines, so not the whole set of tutorials can be run there, because some of them, if you run on CPU, takes forever. But a subset of them, you can try them without installing CNTK or do anything with it. This is CNTK's GitHub page. Basically, you can see that I highlighted 4 folders that are really great learning material. The first one is examples. So in CNTK, we have created a large number of examples in this folder. The criteria of being an example is that it has to be some relatively well-known deep learning algorithms, for example, like ResNet or Inception v3, or faster RCN, for example. And also, anything we put in the examples, all the scripts, has to be very carefully verified to the level that we make sure that if you run these scripts yourself, you should be able to obtain same or even better accuracy than what the original paper of this example come from. Just to give you an example, like Inception v3, if you take Inception v3 model from this example folder, you actually will be able to train an Inception v3 model with CNTK with accuracy that's about like 0.5% higher than the original paper of Inception v3. Now, these verification steps takes a long time for us to do, and we really want to make sure that anything we share here is going to be high quality. And the second folder is called a manual. This one was recently added in v2.1. So these are essentially a list of manuals explaining how you can use CNTK. For example, how do you feed the data into CNTK? How do you do debugging with CNTK, etc. So these are all Python notebooks that you can go through and learn how to use CNTK. We also have a pre-trained model folder, which contains a bunch of pre-trained models. Some of them are converted from Caffe. Some of them we trained from scratch with CNTK. By the way, we have a Caffe to CNTK converter, a model converter, so we can take some of the existing Model Zoo Caffe models and directly convert them to CNTK. And the fourth folder is the tutorials that I just talked about. We also have a pretty concrete list of documents. It's basically sits currently on doc.microsoft.com, and you can navigate there to find out whatever that you're interested in to learn. This is the Python API documentation. It's very clean, and you can find most of the stuff you want to find. So what exactly is CNTK? CNTK expresses nearly every or arbitrary neural networks by composing simple building blocks into complex computation networks. So let me give you a very simple example here. So bear with me a little bit. This is a little bit of math. So for those of you who understand the kind of the very basic deep learning model, which is a multi-level perceptron, it essentially, this is a very simple one of 2 hidden layer feed-forward network. You got a input that is x. You multiply the x with a weight, add a bias, and then pass through the output to a nonlinear function sigma, and you end up with the output of the hidden node, which is h1. That's the first hidden layer. And then you take the first hidden layer's numbers, and then you do the same thing. Multiply a weight matrix plus the bias, run through a nonlinearity, you get the second hidden layer. And then the third one, you basically just multiply W out plus a bias, and then going through a softmax will produce the output for this particular network. So this is probably the simplest, one of the simplest neural network models you can use. With input x, and now you also need to define a one-hot label vector. So let's say I'm doing, say, car detection or flower detection. So you got 100 type of cars that you want to classify. So the one-hot label is going to be a 100-dimensional vector, which is mostly 0 except a 1 that's kind of the exact type that this particular image corresponds to. So you got a bunch of zeros and ones. And then you can calculate a loss function, which is essentially what the neural network trying to optimize by calculating this cross entropy, which is y transpose log of p. So these are all math equations. And on the right, I'm showing how you can convert these math equations into Python code. So x at W1, at here is matrix multiplication introduced in Python 3.5. You plus a bias B1, and then you go through a sigma function, and you get H1, right? So you write this Python, 4 lines of Python code, which is extremely easy to understand and straightforward. So taking these 4 lines of Python code, what CNTK does is it's going to convert these 4 lines of code into a graph. So here you can see that the operator or the functions that's being used in these equations or Python code is going to be a node in this graph, like multiplication or plus or the nonlinearity. And then the weight matrix, the bias, and the input and output are essentially data flowing in and out of this graph. The reason for constructing such a graph is actually very simple. We want to do automatic differentiation. So if you want to calculate the derivative of a loss function over a input, in algebra there's a very well-known rule called the chain rule, which basically says the derivative of a loss function over the input is the same as if you calculate the loss function derivative of the loss over some output, and then derivative of the output over some input. So this is automatic differentiation. And with a graph, essentially, every node, you will be very easily to tell who is your parent, who is your child, and therefore the automatic differentiation can be done relatively easily. And after all this graph has been constructed, CNTK then really invokes the execution engine. And then now we can actually run this graph and do some training. The graph is editable, it's clonable, and you can think of it like a Lego. Basically, you can take some of these functions out, maybe replace it with something, and build some new graph. So this composability really allows CNTK to support a wide range of networks and applications. So if you want to work with CNTK, here are the 5 steps usually you want to take. So the first thing you need to do is you're going to prepare your corpus or your data, right? So you want to handle your own data. So the first step is to collect data and maybe make it in a format that CNTK can understand. And then we need to write a reader, which basically reads the data from wherever you store the data. And this reader can be a CNTK built-in reader, or it can be just your own Python code that converts your data into a NumPy array and then feed it into CNTK. After you define the reader, then you define a network. And this network, it is essentially your model. This is your being a multi-level perceptron, or it's AlexNet or ResNet. Essentially, that's your network. And then after that, you define your trainer, which is how you want to train this network using, say, statistical gradient descent or using some Adam algorithm. And then once you define everything, you call train, and then it will generate the model that you're looking for. So writing CNTK code in Python is actually rather straightforward. And you can see this is kind of the boilerplate of essentially what you're going to write in Python. You're going to write a reader, like create a reader, and then you're going to create a model, and then you define a function that creates the loss function, the criteria. After that, you define a train basically function that will do the training, and the evaluation function that will do the evaluation. So the main function calls are essentially create a model, create a reader, do the training, create another reader for evaluation, and then do the evaluation. And once that is done, all you need to do is basically call Python, my script, and then you are ready to go. So let me go in a little bit more detail. So for readers, CNTK has a bunch of built-in readers, and they are basically based on a class called a mini-batch source. So in this particular case, I'm showing you a mini-batch source for image reader. So assuming you have a lot of images, like ImageNet, you want to load your images and trying to do some training. So you define essentially a set of features that's based on image, and then define your labels. And the CNTK also natively support a bunch of automatic randomization and data augmentation. So you can do cropping, scaling, jittering, etc. And basically all the popular ImageNet models, we all do this kind of image enhancement. So this randomization will be done automatically by CNTK on the fly, and you can also apply it to really large data sets. And the reader is also composed, which means you can write 2 readers, one reading an image, one reading a text, and you can compose them together. Once the reader is written, you want to prepare your network. And in this particular case, let's say we want to write a simple multi-layer perceptron. And so you got a model that's something like this. It's a 3-layer, very similar to the one I just presented. You got 3 dense layers, and so writing in Python is extremely simple to do. And then this is your loss function. We can also write other networks like a convolutional neural network. So here is a very simple example of a 2 convolution layers followed by max pooling and then dense layer. So this syntax is actually nowadays almost every toolkit kind of following very similar patterns. So it's very easy to use. Now, one of the strengths of CNTK is to handle sequence data. So just to give you an example, what kind of problem we can solve. This is a many-to-many sequence mapping example. The input is essentially a sentence saying, show Burbank to Seattle flight tomorrow. What this neural network, this recurrent neural network trying to figure out is to say, hey, which city is a from city, which one is a to city, and what is the date. Right? So, and in CNTK, writing a recurrent network is as simple as writing the other non-recurrent ones. So in this particular case, you basically write a 3-layer recurrent network having an embedding layer at first, and then followed by a recurrent LSTM layer, and then a dense layer. So after writing the models, the next step is to prepare your learner. And there are many built-in learners in CNTK. We have statistical gradient descent, SGD with momentum, ADA grade, IMS prop, ADA max, ADA delta, etc. And for those of you who have been doing a little bit deep learning already, you know that it's quite important to specify a learning rate for deep learning. And in CNTK, you can define a learning rate schedule and a momentum schedule, just as the code underneath. So in this particular example, we're defining a learning rate schedule. Basically says for the first 3 epochs, you want to use a learning rate of 0.05. And after that, for the next 2 epochs, you want to use 0.025. And the remaining of the epochs, you want to use even smaller learning rate. And then you say, I want to define a SGD learner, and that's all you write. So here's the overall train workflow. You first write a model. You define your loss function. You want to write an error function because typically in deep learning, you want to test your model on some validation data set. So you write a classification error function. You choose a learner. And then you define a trainer that combines the model, the loss, the error, and the learner. And then you say trainer.train minibatch. X and Y, X is the input, Y is the one-hot label, for example. Now, if your problem is really large, then you want to train it in a distributed manner. And CNTK is really strong in this area. So configuring CNTK to train distributed manner is extremely simple. So we're basically using MPIs here. So you have basically calling MPI -MP, the number of GPUs, the number of the list of hosts, and then you basically put your kind of a local training script there. Maybe change 1 or 2 lines of code, and you're running on 16 GPUs in parallel across 4 machines. All right. So now I'm going to tell you a little bit about some of CNTK's unique features. These features are unique in the sense that no other toolkit has them, and these are also the reasons why CNTK is so much faster in recurrent network, so much better in distributed training. So these 3 unique features are symbolic loops, parallel training through mini-batching for sequences, and unique parallel training algorithms like 1-bit SGD or block momentum. So looking at sequences, let's think about what happens if we want to have a network that handles sequence data. In that particular case, we need to introduce the concept of time. And so on the left, are the basic equations that I just showed you in the previous example. Now, if I want to make it a recurrent network, here are the modifications I need to do. Essentially, the input x now is a function over time t, and then the hidden state of time t is not only going to depend on the input x over time t, but also depend on its previous state, which is ht minus 1. So the math equation here stays very simple. you introduce two new matrices, R1 and R2, to represent what you want to do with your hidden state. And then you have pretty much everything the same as before. In CNTK, we introduced this particular keyword called past value. So past value of H1 is essentially H1 t minus 1. So writing in Python code, you just say past value of H1. You can also write past value of H1, which means H1 t minus 2. So in terms of code, basically it's rather straightforward. Maps very well with the math equations you would want for sequence handling. And taking this new Python code, what CNTK will do is to introduce a few loops inside the graph. And this is very unique in CNTK. None of the other toolkits will contain loops in this manner. So you can see basically the highlighted ones, the red circles are the new loops introduced by CNTK. And this is a very compact representation of recurrence. During execution, CNTK will automatically unroll these circles at execution time. And the circles are being detected with Tarjan's algorithm. And this is extremely efficient and composable. The second idea, very unique feature inside CNTK is batching. So let me explain the concept a little bit. When you handle sequences, let's say we are doing natural language processing. The input data are usually at the level of sentences. So some sentences are going to be pretty long, let's say 20 words, and some sentences can be really short, like 2 or 3 words. So when you doing parallel training across multiple sequences, the simplest way is to stack these sequences side by side. So basically, because GPU is really good at the parallelization, you can execute these sequences simultaneously by looking at, for example, the first word of sequence 1, 2, and 3 all together at the same time on the GPU. The problem with this kind of setup is that in a true realistic natural language processing task, these sentences are of very different lengths. And in this particular example, sequence 2 is much shorter than sequence 1. And therefore, the execution of sequence 2 is going to finish much earlier, while sequence 1 is still computing. And then as a result, the GPU computation unit that's kind of being tasked to do sequence 2 will become idle once sequence 2 is finished. And this basically reduces the utilization of GPUs. All the other toolkits handle this problem by asking users to do manual bucketing, which essentially says, you're the user, please just give me a set of sequences that are of similar lengths. The issue with that is now the user is going to interfere with the randomization process of the sequence processing, which tends to reduce the accuracy. So in CNTK, we use a different trick. Essentially, we take the longest sequences and then we examine whether two other sequences added together would be of shorter length than the longest one. So in this particular case, we're putting sequence number 3 right behind sequence 2 to execute. And this is an example of packing basically 7 sequences to compute with 4 GPU computation unit. And you can observe that the amount of padding we will add is much smaller than if we don't do this. So in CNTK, this batching process is completely transparent. The user basically writes sequence process based on a single sequence, and the CNTK automatically does everything for you. This, although looks quite simple, it's actually, when you implement it, it's actually quite challenging. Mostly because when you cross the state between, say, sequence 2 and sequence 3, because it's a recurrent network, so all the state of the hidden layer, etc., all need to be reset. And when you do a sequence reduction, masking has to be done properly to make sure the return results are accurate. So, so this feature, basically this batching feature, has been in CNTK for a couple years, and so far we're still the only toolkit that's able to implement this kind of feature, and that's why we're still enjoying 5 to X speed up compared with any of the other toolkits out there. And the third unique feature is about data parallel training. So let me give you a simple explanation of what you would do with data parallel training. So data parallel training is kind of one of the simplest way to run deep learning tasks across multiple GPUs. So take a large chunk of data. Essentially, you can cut this data into multiple pieces and say, each of the node, please take care of one of these pieces. Right? So you take this data, you send it to 3 nodes in this particular example, node 1, 2, and 3. Each node will have an initial state of the model, and then it will take its own data and then start training. And this training typically involves, say, a forward pass that will run from the input to the output, and then a backward pass that will calculate the gradient of the network based on the data. Once all the gradients are calculated by all the nodes, typically, this is kind of the most naive way, you can run a all reduce on one of the nodes, like in this case, node 2. So essentially, all the nodes, 1, 2, 3, send their gradient to a single node. You sum all the gradient up, update the model, and then you send the model back to all the other nodes to continue training. And this is very inefficient because essentially we created a bottleneck, a choking point. If node 2 fails, then the whole process is really going to suffer. And also, node 2 requires a huge amount of bandwidth in order to suck in all the gradient and send out all the models. So a better way is to cut your deep learning, the model, into multiple chunks as well. So in this particular example, this is actually a quite well-known algorithm called the ring algorithm. Essentially, you cut your model into 3 pieces as well, and each node is now responsible to aggregate one chunk of your model. So in this case, node 1 is responsible to aggregate the first 1/3 of your model. Node 2 is the second third, and node 3 is the third part. So node 2 and 3 will send their gradient of the first part into node 1, and node 1 does the aggregation, and then send it back to 2 and 3. This algorithm is called the ring algorithm. It has a very nice property that the total amount of data being transmitted across all the nodes is 0.1 with respect to the total number of nodes you have. This is so nice because if you want to scale to, say, 1,000 GPUs, the total amount of data being transmitted across the nodes is constant, essentially. When we started doing this distributed training for speech workloads, we realized that this kind of ring algorithm, even though it's 0.1, it's still not enough. Let me give you a simple example here. Let's say you have a deep neural network with a mini batch size of 1024. You have a model of 160 million parameters. So computing this model, let's say on a Titan X, will take you about 1/7 of a second. However, the amount of data you need to communicate, which essentially includes the gradient, which is the same size as the model, is going to be 640 megabytes. And you're transmitting over PCIe, so 6 gigabytes per second. And so the communication cost per mini batch is about 1/9 of a second. So it's very obvious that you cannot even parallelize this task onto 2 GPUs, because once you have 2 GPUs, the amount of compute per mini batch will scale down by a factor of 2, because now you split the load into 2 GPUs, and therefore compute will finish in 1/14 of a second, yet your communication stays the same, 1/9 of a second, and it's already kind of the majority time you're spending on communication rather than doing any computation. So in CNTK, we have included a bunch of algorithms that can reduce this communication cost, and these are rather novel algorithms. So the first idea is to communicate less each time. Instead of sending 32-bit gradient across different nodes, we're sending 1-bit gradient with a trick that we carry over the quantization error to next mini batch. We can also communicate less often by automatically increase the mini batch size or adopt a new algorithm called the block momentum. I don't have time to go into details of each of these algorithms, but you're welcome to just go and read these papers to understand what are the ideas behind these algorithms. So one thing that this September we have released is CNTK C# API and R bindings. Let me take 5-10 minutes of time to explain to you what we have done for these two APIs. So C# API is really nice because in many of the production loads, at least in the Windows ecosystem, many applications, they choose to use C# to do data pre-processing, right? So you got a bunch of data sitting in either SQL Server or some other places, and you process them with C#. But most of the toolkits out there, the most popular interface is Python. So now you need to either duplicate your data pre-processing code in Python, and which is very error-prone, or you somehow bridge these two languages, which is inconvenient. So we got a lot of requests of creating a C# API for both training and evaluation. So as of CNTK v2.2, we have introduced the C# API, which can do both training and eval. So it supports building of deep learning networks, it supports training, supports eval, and we provided a number of end-to-end examples in C#. So I mentioned earlier that CNTK is primarily implemented in C++, and that gives us a unique advantage of creating this C# API because we can basically use Swig to convert most of the C++ functions into C#. And therefore, basically you get probably one of the most complete C# APIs you can find out there. We have over 100 basic operations to build a common computation network, including things like sigmoid, hyperbolic tangent, ReLU, etc. And you can, for example, write a logistic regression loss function in 2 lines. So just give you an example here. Basically, you have this operator called times. So you're multiplying a weight parameter with the input, adding a bias, and then you define a loss with a single line, cross entropy with softmax. You can also use CNTK function as a primitive element to build novel DNNs. Here I show example building a basic block for ResNet. So here you basically include a convolution, pooling, and then a rectified linear unit, and a bias plus. And so 2 lines of code, which is extremely compact, and you practically have a building unit for ResNet. So implementing the whole ResNet would be actually rather easy to do.
Question.
Yes? Would you like to use the microphone, or?
Yeah.
Thank you, because it's being recorded, so.
There it goes. Can the Cognitive Toolkit be used within the Visual Studio development environment?
Yes, that's a good question. Actually, we just announced basically a Visual Studio Code plugin that essentially help developers to do AI develop. That will have basically built-in support for CNTK.
And do you have a link that would provide some kind of a textual or some kind of an example that you could walk through for that?
For the plugin or for code of C#?
For the code itself.
We do have a bunch of code, which I will have a bunch of links in this slide deck that covers a bunch of examples. I will show you in the next few slides.
Okay, thank you.
Yeah, thanks. CNTK C# API supports batching, so the native mini-batch source, everything is there. We support training, all kind of learners. So here's an example of writing a ADAM, stochastic optimizer. Just writing a parameter learner as a list, and then do create a trainer with that learner. So here I give you an example of how do you write, say, a classification example. We want to classify handwritten data. So you can build a convolution model by composing a number of basic ops. You prepare the data with the built-in reader, like the mini-batch source, and then you do training. Right? So you create arguments of this dictionary, which contains the input data and the label, and then you train with this mini-batch. So this is the list of examples that we have included. You go to examples, training C#. We have logistical regression, the MNIST example I just briefly went through. We also have a sci-fi ResNet classifier, a transfer learning example, which I think will be very popular because for most of the applications done by third-party customers, they seem to request that they have a relatively small amount of data, so they want to do a transfer learning from a pre-trained, very large data-trained model to a set of smaller data and be able to do either classification or detection. And we also have an example to do a LSTM sequence classifier. R binding is also new. We actually made it public right at this Ignite. So to install R binding, it's very straightforward. DevTools, install GitHub. We have a comprehensive set of coverage for CNTK functionality, including readers, layer library, loss functions, normalizers, optimizers, model saving and loading, etc. And these are exposed via the idiomatic R function API. And these will interop with R objects and packages like ggplot. And it also supports fluent syntax for constructing layers based on mag tree. It's a high performance. Essentially, I think it's maybe 5% slower than native Python, and including support for multi-node and multi-GPU training. So this R binding is written based on reticulate package. Essentially, it enables importing and calling Python functions directly from R. We have full parity with Python bindings because the Python layers are very thoroughly tested. So we make sure that this R binding is as accurate as it should be. And it does enable interop between R objects and NumPy. It does require full installation of Python bindings. And of course, I shall mention that converting back and forth between Python and R can be expensive. But if you're using, say, everything built in from CNTK, like all the readers and trainers, then you will incur no penalty, and everything will run extremely fast. Just to give you an example, this is a sci-fi 10 training example. So you import a bunch of libraries, and then the reader can be defined. This is all R syntax, very close to Python code, actually, look at it. And you define features and variables, and you can normalize features. You can define a model. So this one is also very similar. Basically, convolution, max pooling, followed by dense, dropout, etc. And then you define a loss function, and then you can initialize the learning algorithm. So then you can run. Notice that the use of this fluent syntax using magic tree pipe notation, which is very good, easy to use. And then we also have integration with ggplot. So in this particular example, you can plot essentially all the loss values over training for all the mini batches. And so you just get this figure. That's very nice to see. For R binding, the future work is we're going to add more examples and vignettes. We're having a tighter R integration, like formula objects, data frames, and matrices, integration of training models with summary and predict generic function, and then integration with TensorBoard. And if you want more information, here's the source code. Everything is open source. And you have vignettes and documentation and issues and feedback. All right. At the end of the talk, let me spend a few minutes talking about what's going to happen in CNTK, the forward-looking kind of roadmap. So I don't know how many of you have heard of this thing called Open Neural Network Exchange. This is a collaboration between Microsoft and Facebook. It's an open source intermediate representation of computation graph. It's out there, https github.onyx. We have defined a small set of common ops that will run, that will be common across CNTK, Caffe2, and PyTorch. And this was released on September 7th, 2017. We already have a shared library with Caffe2 example as a reference. The whole Onyx thing is MIT license with no patents. So the motivation of creating such a exchange or model format is, one is certainly to allow interoperability between frameworks. So you can, for example, train with a CNTK toolkit and then save the model into this format and then do inference on Caffe2, for example. We also allow the hardware vendor to focus on one single intermediate representation in their backend, which make their life a lot easier. We allow so the third one I already mentioned, you can train in one toolkit and deploy in another. So here's the kind of the overall vision of the Onyx. We have the Onyx thing in the middle, and then we have Microsoft backend, we have Facebook backend, and we may have other toolkits backend, which will run then on top of CPU, GPU, FPGA, or even custom silicon. And then on top of the Onyx, we have a CNTK API, Caffe2 API, PyTorch API, etc. And then, of course, one layer up is all the C++, C#, Python implementations. So here's the current status. V1 of Onyx has been released in GitHub. This is a minimum set that Facebook and Microsoft can agree upon to release. Currently, it only supports inference. There's no loop, no RNN existing. Caffe2 and PyTorch already support such a format. CNTK support will come early October. In V2, we expect to add RNN support, loop and control, and add a model zoo that can be shared across all the different toolkits. And of course, we're looking forward to more support from other toolkits or other frameworks. Let me mention a few other upcoming new features in CNTK. The number one is a model optimization and cogen framework for fast inference. So one of the things we learned when talking to all these first-party Microsoft customers is that they really care about running these trained models fast in order to really ship that into, say, Bin or Cortana. So CNTK will add a support for model compression via SVD or weight quantization. And then we will work on a fast inference framework through Cogen. For those of you who have been using CNTK before, you probably already know that in V2.0, we introduced one-bit convolution, which is through the Halide framework. And this is an extension of that work, and we'll make it happen in the coming months. The second thing we're working on is a C# API for training. And this one, we already released a low-level C# API in V2.2. We're still refining it based on some feedback from GitHub. And then we are in the process of designing a high-level API that will make this whole C# training and eval extremely easy to use. And this is in our pipeline. We are also working on something called a crosstalk. So this is also, we got feedback that a lot of the existing models on the internet are based on other frameworks. So we would like to port models created from other toolkits to CNTK. And that probably include like Caffe, Caffe2, TensorFlow, etc. And this is ongoing work. I think we already have crosstalk for Caffe. And we're going to use Onyx essentially as the intermediate representation for doing all these conversions. And the second to the last item is dynamic graph support, which is very popular, mostly for its debugging capability, like what PyTorch do, but also you basically can create different graph for every training example. And so we want to enable that in CNTK, and this is still ongoing work. we're still, it's probably going to be ready somewhere next spring. We'll see. And then the last item is we're going to create more examples and better documentation, which is also a big request. So conclusion, CNTK is a very high-performant toolkit. Its speed is very fast. It's 5 to 10x faster on recurrent networks. It can use just a few lines. You can have scalability across thousands of GPUs. We also have these built-in readers that make sure that distributed learning can be done very efficiently. And in terms of programmability, we have full powerful C++ library for enterprise users. And we have Python, C#, R, Java, etc. And CNTK itself is also very extensible via custom layers, learners, readers, etc. So that's all I have. Go to GitHub and try CNTK and give us some feedback. Thank you.